before we continue talking about chapter 4 stuff, a few people had asked if we could kind of revisit some things from a couple weeks ago, which I'm happy to do. Specifically like inverse trig stuff and some what's what I'm looking for. Logarithmic differentiation and related rates. I had one question for all of you about whether or not there's something you've covered. So let me ask you all this kind of question, and then I'm gonna continue on. So yeah. Have any of you seen something that looks like this? The derivative of f inverse at say b is equal to 1 over f prime of f inverse of b. Don't look familiar at all. Okay, all right. So I guess we should talk about this for a minute. I will tell you, this is a theorem that doesn't get used, in my opinion, a whole lot. You can use this to find the derivatives of the inverse trig function, or really any inverse function. But again, there are usually nicer, more straightforward ways. And yeah, cool. So another way of writing this is that the derivative of f inverse evaluated at x equal to b is equal to 1 over the derivative of f evaluated at x equal to f inverse of b. I'll be perfectly frank, this theorem really kind of used to trouble me. Like I was like, why does this work? Like you just divide by the derivative and you kind of change things up a little bit. And you can certainly make it work if you use the chain rule, right? You can say that f, sure, f of f inverse of x is equal to x, and then differentiate both sides. We don't really, I mean, sure, fine. F prime of your stuff times the derivative of f inverse of x has to equal 1. And then you divide both sides by this. And oh, look, you get exactly f inverse of x derivative is equal to 1 over f prime of f inverse of x. Cool, but not super helpful, right? Like this doesn't really tell you a whole lot other than the formulas. So I would really love to do an example for you all to kind of help me understand why this actually works the way it works. So let's look at the following example. And then maybe we'll throw a question or two at you about it. So let's say we had, and if you, sorry, let me make sure you're not missing that if you want it there. So here's the example I've got. Let's first start by graphing very kind of easily f of x equal to x cubed plus 1, and also the inverse function, which you may or may not actually find. So, not going to graph all of it. I know that the cubic graph has the usual shape. I'm just going to shift it up 1. So instead of getting the point 0, 0, I'm going to get the point 0, 1. I'm going to get the point 1, comma 2. And I would get the point 2, comma 9. Sure, up here. And then I also have the point negative 1, 0, and negative 2, negative 7. So it'll look kind of like this. Yeah, not the best graph ever, doesn't need to be. So I've got 0, 1, negative 1, 0, 1, comma 2, and 2, comma 9. And lovely. If you're pressed for time, you could just graph the inverse by literally interchanging x and y. So I want to graph the inverse, I'm just going to change all my x and y. So instead of getting 0, 1, I'm going to get 1, 0. Instead of getting 1, 2, I'm going to get 2, 1. Yeah, okay, that's right. Instead of being 2, 9, I'm going to get 9, 2. And instead of negative 1, 0, I get 0, negative 1. So it kind of looks like this. Okay. Now, here's the question I'd really like to ask, or I'd like to explore. How does the slope of f of x at x equal to 2, let me draw that in for you, right there. How does the slope of that tangent line compare to the slope
of f inverse of x at x equal to 9. So over here.
Let's find out.
So the first part of that question is easy. F prime of x is equal to 3x squared. If we plug in 2, f prime of 2 is equal to 3 times 2 squared, which is 12. To find the other question, the answer to the other question, I guess I better actually find the inverse function. So we find the inverse function. I'm going to start with y equal to x cubed plus 1. I'm going to interchange. Solve for y. X minus 1 is y cubed, and the cube root of x minus 1 is equal to y. So my inverse function is the cube root of x minus 1, or if you prefer, x minus 1 to the 1/3 power. The derivative of this is equal to 1/3 times x minus 1 to the negative 2/3. If we plug in 9, we see that the derivative of f inverse of x evaluated at x equal to 9. We don't plug the 9 in there because it looks like you're kind of doing the function first and then differentiate after, and you get 0. We're going to get 1/3 times 9 minus 1 to the negative 2/3. 8 to the negative 2/3 power. Okay, let's see. 8 to the 1/3 power is the cube root of 8, which is 2. 2 squared is 4. 2 to the negative second is 1/4. So look, we get 1/3 times 1/4, which is 1/12. So the thing I want you all to see here is that the derivative of the function here at this point is equal to the reciprocal of the derivative of the inverse at the corresponding point. And that's what this theorem that I just talked about, or that I showed you, actually says. It says that the derivative of f inverse at a point is equal to the reciprocal of the derivative of the original function at the corresponding point. That's the whole idea of the theorem. Yeah. So then we could ask questions. All right, let me back up. Let me pause for a second and ask, are there questions about this? Yeah. Sure. So let me just say the things again. So what we're really saying here is that if someone asked me in this problem, if someone gave me this function f of x and said, find the derivative of f inverse of x evaluated at x equal to 9. What we could do instead of finding the inverse function, we could say is, well, I know that instead of finding the derivative of the inverse function over here, I can find the derivative of the original function over there and take the reciprocal of it, because this slope and this slope are reciprocals. If this is really, really positively big, this is going to be really, really positively small. This one was 12, this one was 1/12. We don't need to know what f inverse is to find that the derivative is equal to 1/12. Sorry, you can't quite see that. Apologies. So check this out for a second. So to find this, I'm going to say, well, that's going to be equal to 1 over the derivative of f of x. I'm evaluating that at x equal to f inverse of 9. Not at x equal to 9, but at the corresponding point that makes sense. Well, what's f inverse of 9? That's terrible. F inverse of 9 equals what? Well, the way we usually actually do this is we say f of what equals 9. Oh, what's the only number that makes that work? Right. The question mark here has to equal 2, because f of 2 equals 2 cubed plus 1 equals 9, which means f inverse of 9 is equal to 2. Okay, So check, and then our derivative, right, f prime of x is equal to 3x squared. So this is going to equal 1 over 3x squared evaluated at x equal to 2, which is going to be 1 over 12. So that's the idea of this theorem, that instead of actually finding the inverse function, if it's even possible to do so, you can instead take the derivative of the original function, evaluate it at the corresponding inverse point, and then take the reciprocal of that. It's kind of neat. It's kind of terrible to get the derivative of the inverse at a point. This is so this is the derivative of the inverse function to that function there at that point. So looking back at our picture, maybe here's the inverse function. And what we're saying is the derivative of the inverse function at x equal to 9 is 1/12. But it's really also the reciprocal of the derivative of f of x at x equal to 2. That derivative there, that slope is 12. And so the derivative of this is the reciprocal of the derivative of that. Let's look at a couple examples and then we'll move on. Again, it's not a super duper important formula, and I'll kind of tell you why after we've done this example, after we've done one example and then one actual thing. So let's say, is that the right one? Sorry. Sure, we'll do one, maybe two. So here's kind of the kind of question that might get asked about this on an exam. Find the slope of the line tangent to the inverse of f of x equal to x to the 5th plus x cubed plus x at the point 3, 1. So I want to point out here, f of 3 isn't equal to 1. F of 1 is equal to 3. And if we could find the inverse function, which we really can't, it is invertible though. This function definitely is invertible. How do I know it's invertible? Because I know it's increasing always. Because if you took the derivative of this, the derivative of this would be 5x to the 4th plus x squared plus 1, which is always greater than 0. And if a function is always increasing, it definitely passes the horizontal line test. It is therefore invertible. Do we know what the inverse is? Definitely not. Could I find it? Probably not at all. Like really, like I don't think you can solve for the inverse here, not without some powerful computer tools. We don't need to because we have this lovely theorem. What the theorem says is that great, f of 1 equals 3 or f inverse of 3 had better be 1. That's the whole nature of inverse functions. They interchange the x and y input and output relationship. So then if I want to find the derivative of f inverse of x evaluated at x equal to 3, that's going to be the same as finding 1 over the derivative of f of x evaluated at x equal to f inverse of 3, which is 1. Cool, and now the rest of this is not terrible. The derivative, as we just mentioned, is 5x to the 4th plus 3x squared plus 1. If we plug in 1, we're going to get 5 plus 3 plus 1, which is 9. So this is going to equal 1 over 9. And graphically, here's what's happening. So just for pretend, if we pretend our function looks something maybe like, we'll go to the point 1, 2, 1, 3, right? Our original function maybe looks something like this. And it's got a slope of 9 at the point 1, 3, then the inverse function has to have the inverse slope at the point 3, 1. So the derivative there is exactly 1/9. That's what's happening there.
Okay. We'll do one more like this, and then we'll do one more thing with this, and then we'll talk about inverse string derivatives again. So here's one that's a little more challenging. Given f of x equal to e to the negative x squared plus x. Find the derivative of the inverse evaluated at x equal to 1. Okay, I'm just going to toss the formula at it. That's going to be 1 over the derivative of the original function evaluated where? Well, we can be very generic. Instead of, like, I don't actually want the number yet. I want you to tell me at x equal to, what's the expression I should be writing over here? It's f inverse of 1. Here's the hard part. What's f inverse of 1? Well, if f inverse of 1 is equal to, let's just pick a letter. Let's call it y. Maybe I should call it x. Oh, well, let's call it x, sorry. Then f of x should equal 1. That is e to the negative x squared plus x is equal to 1. All right, and here's the fun part. You get to guess. There's no solving here. There's no like trying to use a logarithm or something. You just have to guess the value of x that's going to make this work. Fun fact, there's not a lot of good guesses. There's not a lot of numbers I can plug into the exponent of e and get an integer as the result. In fact, I can only think of one number. What's the number you can take e to the power of and get a nice whole number? E to the 0. What's e to the 0 equal to? Cool. So e to the 0 plus 0 definitely is equal to 1. So that means f inverse of x had better be, f inverse of 1 had better be 0. So the f of 0 is equal to 1. And now we're pretty much good to go. We still have to find the derivative, I guess. The derivative of f df dx is equal to the derivative of e to the negative x squared is e to the negative x squared times negative 2x. The derivative of x is just 1. Plugging in 0, yeah, plugging in 0. df dx evaluated at x equal to 0 is going to be e to the 0 times 0 plus 1, which is just 1, which is not very exciting, but oh well. So their answer here is going to be 1 over 1. Oh, sorry, yeah, sorry, yeah. Sorry, yeah, the derivative value x equals 0 was e to the 0 times 0 plus 1, which is just 0 plus 1, which is 1. And then we plug that back in right there. And then we get 1 over 1, which is 1. It's kind of boring when the answer is 1 over 1, because it's like you feel like you didn't really need to do that, but you did. Okay, so now one could use this formula to find the derivatives of inverse functions, like the inverse trig function, or the natural log of x as the inverse of e to the x. But we don't use it. But let me show you one time how we could, and then we'll kind of not do that anymore. So let me show you one example here. So we could use this formula to find for f of x equal to, let's do sine of x, sure. Yeah, f of x is sine of x. We want to find the derivative of f inverse of x. All right, so here we go. I'm just using the formula. The derivative of f inverse of x is equal to 1 over the derivative of f evaluated at x equal to, this is where, so this is where I need to be a little bit careful here. I'm going to use a different letter. So let's call this, sure. Sorry, let me think for a second about how I want to phrase this exactly. Yeah, let's call this theta equal to f inverse of x.
All right, so let's find our derivative. Our derivative of sine of x is just cosine of x. What about this theta equal to f inverse of x? So here's what I really want to do. I'm going to have 1 over sine, not sine, sorry, cosine of not x, but theta. Hold on for a second. This looks kind of weird. Theta is equal to my inverse function, which is the inverse sine of x. So this is equal to 1 over cosine of inverse sine of x, which is technically a correct way of writing this answer, but not how we're going to leave it. So here's what we're going to do. We're going to talk about how inverse sine of x is an angle. And we're going to do the usual triangle thing. So sine of theta is equal to x over 1. This third side is the square root of 1 minus x squared. And cosine of inverse sine of x is the adjacent over the hypotenuse. So cosine of this angle is going to be the square root of 1 minus x squared over 1. Hey, look, there's your derivative of inverse sine. Done the least nice way possible, in my opinion. But it's true. It does work. You could totally weirdly use this formula every time you wanted to find the derivative of an inverse trig function. But I don't think you should. Cool. So again, it's a useful formula. It comes up occasionally. I wouldn't spend more time than I've spent talking about. Like, I think we've talked about too much already. I just talked about for the last, 20-ish minutes. It's more time than you should really think about this function or this theorem. Let's continue on with the inverse trig functions. Let's talk about finding the derivative. I know we've talked about them already, but I'm just kind of reviewing them. Let's talk about finding the derivative inverse cosine the other kind of usual way. So to find the derivative of the inverse cosine of x, instead of saying it's 1 over negative sine of inverse cosine of x, which is what the formula would be, right? So it's not going to be 1 over negative sine of the inverse cosine of x, although that would be a way of doing it. How am I getting that? By the way, I'm saying, oh, the derivative of cosine is negative sine, and it's negative sine of f inverse. This is your 1 over f prime of f inverse. We'll do the usual thing, or what I think of as the usual thing, where we're going to say we're going to let y equal the inverse cosine of x. And then we're going to get rid of the weird function or the problem function by replacing, or not replacing, by taking cosine of both sides. Cosine of y is equal to x. We're undoing the inverse, right? If y equals inverse cosine of x, then cosine of y is equal to x. Or as I read this, the inverse cosine of x is the angle that if you took cosine of that angle, you would get x. And that's exactly what we're writing down here. That's the angle that if you took cosine of that angle, you would get x. And then we differentiate both sides implicitly. Derivative of cosine of y is negative sine of y times the derivative of y with respect to x. The derivative of x with respect to x is 1. And then you're going to get dy dx equal to 1 over negative sine of y. Hey, look, that's your 1 over negative sine of the inverse cosine of x. How neat to see that those are really the same sort of thing. And then lastly, I'm always going to draw my triangle. My angle is y. And we know that cosine of y is adjacent over hypotenuse. And then we can find this third side. I've done this so many times, I just know what it is, but it's probably good to show the work. So I call this third side z for a second. X squared plus z squared equals 1 squared. Z squared equals 1 minus x squared. Z is equal to the square root of 1 minus x squared. Technically, there's a plus or minus there, but we've seen enough times that we always get the thing we want, so we're not going to write it. We always get the nice plus or minus that we need. So here we're gonna get that this is equal to 1 over negative sine of y is z over 1, or the square root of 1 minus x squared. And not surprisingly, which we've seen before, the derivative of the inverse cosine is just the negative of the derivative of the inverse sine. So the derivative of inverse sine of x from before is equal to positive 1 over the square root of 1 minus x squared. And we just saw that the derivative of the inverse cosine of x is equal to the negative of that. And inverse trig functions all have this pattern where the one that's not the cofunction is positive and the one that is the cofunction has a negative derivative, which is cool. So we're not going to derive the rest of them because we've talked about them before, but I will state the rest of them just to kind of have them in our wheelhouse. But here's what we've got. Oh, come on. We have that the derivative of the inverse sine of x is equal to 1 over the square root of 1 minus x squared. You can also use arc sine, right? So you can use inverse sine. You can also say the derivative of, say, arc cosine, if you prefer the arc notation, is negative 1 over the square root of 1 minus x squared. Next up, we have tangent and cotangent. I should say arc tangent and arc cotangent. The derivative of the arc tangent of x is 1 over 1 plus x squared. The derivative of the arc cotangent or the inverse cotangent. I'm just switching back and forth. Either notation is perfectly acceptable. You should use either one and both as you will. It's going to be negative 1 over 1 plus x squared. And then I don't remember if in Grosvenor we ever settled on which version of the arcsecant we preferred. Did McDonald talk about which, or did he talk about, did any teacher talk about the derivative of arcsecant? Did it have an absolute value in it? Yeah, okay, cool. Then we'll go with that one. So the derivative of the arcsecant or the inverse secant of x is 1 over the absolute value of x times the square root of x squared minus 1. And similarly, the derivative of the arc cosecant of x is the negative 1 over the absolute value of x times the square root of x squared minus 1. I will just say again, as I said before, the absolute value is dependent upon the way someone has decided to define the inverse function in the first place, which is kind of unfortunate. But if in your class your teacher said, we're doing it this way, then that is what you should do. Well, it's optional. It is really so. Depending on how the person has defined the inverse secant function, you can get an absolute value there or not. So it's really kind of funky because there's no consensus in the mathematical world on how we define the inverse cosecant and the inverse secant. And so depending on which way we decide to define it, you get an absolute value there or you don't. So you should just do whatever your teacher has said you should do. Because they're like, well, we're going to decide this, and that's what we're doing. So then we could ask questions like, if you look at my notes here for a second before I get too carried away. Where'd you go? Why am I looking at this? Sorry. Sure, like, what's the derivative of the inverse tangent of x squared over x cubed plus 1? That seems awful, but we can do it. So it's going to be the bottom times the derivative of the top. The derivative of the top, we have to use the chain rule. So we know the derivative of the inverse tangent is 1 over 1 plus x squared. The derivative inverse tangent of some stuff is going to be 1 over 1 plus your stuff squared times the derivative of your stuff. Then we subtract, and then it's the top times the derivative of the bottom, which is 3x squared, all divided by the denominator squared. And yeah, that looks pretty gross. We could probably simplify it, but that's really not the point. Let's look at a couple more examples. Let's say we wanted to, that one might have been a little bit kind of wonky. Let's look at something that's maybe a little less ridiculous. Let's say we wanted to find the derivative of the, oops, no, that's fine. Of the inverse cosecant of x to the 7th plus 9x squared plus. I'm just looking at my formula. I know the derivative of the inverse of the inverse cosecant is -1 over the absolute value of x times the square root of x over minus 1. So the derivative of the inverse cosecant of some stuff is going to be -1 over the absolute value of my stuff times the square root of my stuff squared minus 1 times the derivative of my stuff, which you could put in the numerator if you wanted to. Or you can put it at the end, times 7x to the 6 plus 18x. Okay. Why don't you all try this one? The derivative of the arc sine of x cubed times e to the x. Give that one a shot. My outlet's the arc sine. What was on there? All right, let's take a look. I know the derivative of the arc sine of x is 1 over the square root of 1 minus x squared. The derivative of the arc sine of some stuff is going to be 1 over the square root of 1 minus my stuff squared. I have to multiply by the derivative of the stuff, which is going to require the product rule. Derivative of x cubed is 3x squared. Leave the e to the x alone. Plus leave the x cubed alone. The derivative of e to the x is e to the x. And if you really wanted to, you could write this more nicely as 3x squared e to the x plus x cubed e to the x. You probably even factor out. Yeah, let's sure. We'll do that over the square root of 1 minus x to the 6th e to the 2x. And if you really wanted to, maybe you were trying to find the critical points of this function. And so then we took an x, whoops, sorry, an x squared e to the x out, and we're left with 3 plus x over there, and the square root of 1 minus x to the 6th e to the 2x over here. And then you could see that, oh, it looks like x equal to 0 and x equal to -3 are critical values for this function. Because those make the top equal to 0. And I don't know about making I don't know about making this undefined. There might be a place where it's undefined. It's hard for me to know because it's hard to see where this might end up equaling 0. Solving that equal to 0 would be not easy, or maybe not even possible. I'm guessing like the only guess I really got though is 0, and like 0 is not gonna work. And there's probably something. I don't know what it is. Oh well. Sometimes you don't know. Yeah. Okay. So what was I gonna say? There was something I was gonna say. Yeah, if I were, bless you, if I was asked this just to find the derivative of this, I would have left it like this. I was just trying to simplify it because sometimes we have to simplify things. So the critical point I'm finding, so if I simplify this, I get x squared e to the x times 3 plus x over the square root of 1 minus x to the 6 e to the 6. And then to find these, I'm finding these by setting the derivative x squared e to the x times 3 plus x over the square root of 1 minus x to the 6 e to the 2x equal to 0. And so by setting that equal to 0, well, I'm setting the top part equal to 0. So either x, so really x squared times e to the x times 3 plus x equals 0. That's going to give me x equal to 0, nothing here, and x equal to -3. Those are the values that make the numerator 0. And then there's probably some value that makes this thing undefined, but that would be. I mean, we could look graphically for a second. So, if I graphed 1 minus x to the 6th times e to the 2x. Yeah, there is a place where that's equal to 1. Sorry, 1 second. Let me get that over to you all. So if we zoom in here, oh, zoom in, James. Right there. But right, so at 0.7729 approximately, you would have another critical point where the derivative of this function was equal to, what's what I'm looking for? It was undefined. Cool. Yeah, interesting. But yeah, that wasn't really the point of this question, so I wouldn't sweat that too much. No one's going to ask you to find all the critical points, something like this, because it's kind of funky. Oops, come back. It's the right way? No, it's the wrong way. Gotta go this way. You think they make it so you like go either way? Like, I can only slide on the screen from this side, slide off. Like, that's the only way I'm allowed to go. It's kind of weird. All right. I had a follow-up here. Oh, I know what it was. Yeah. You would like to see the things, maybe. There you go. So this kind of leads me to something else, which we never really talked about. And again, not super duper important, but I want to give you one example. Let's say we were asked to find, so find f prime of x for f of x equal to, let's make it really, really super awful, x to the 4th times the arc tangent of x cubed over cosine to the 4th over fine, of x times the square root of x squared minus 7. That looks terrible. And it is terrible, right? It doesn't just look terrible, it is terrible. You could totally find the derivative of this using all the rules, right? You'd use the quotient rule and the product rule a couple of times and the chain rule like 3 or 4 times. But there is another way. Even though this function doesn't absolutely require it, this is a prime example of when you might want to use the process of logarithmic differentiation. I normally wouldn't. Like, if I saw this on the test, I probably wouldn't think to do logarithmic differentiation unless someone told me to. I would do it the hard way. But if you see something that's awful, that often means they want you to use logarithmic differentiation. So here's what we would do. I would write this as a y instead of an f of x. And I would say that the natural log of y equals the natural log of all of that garbage. Let's change that 4th power to a 9th power. is to have a different power. And then I would write that as x squared minus 7 to the 1/2. Okay, here's what I think you should be able to do. We know that all the things in the numerator are going to be positive logarithms, and all the factors in the denominator are going to be negative logarithm of that factor. We could probably even pull down the powers. I think if you feel comfortable, you could jump straight from natural log of y equal to natural log of all this garbage to natural log of y equal to positive 4 natural log of x plus the natural log of arctangent of x cubed. There's no power to bring down there, unfortunately. Minus 9 times the natural log of cosine of x minus 1/2 times the natural log of x squared minus 7. But if you're not comfortable doing all that in one step, I understand. The intermediate step that I would probably take would be the natural log of x to the 4th plus the natural log of arctangent of x cubed minus the natural log of cosine to the 9th of x minus the natural log of x squared minus 7 to the 1/2 power. And now that we've gotten to this stage here, we've made the right-hand expression into as many logarithms that are as simple as possible, so that now we can differentiate both sides without too much effort, without having to use the product and the quotient and the chain. We still have to use some of them, but yeah. So taking the derivative, we also have to make sure we look at the left-hand side here. So the derivative of the natural log of y is going to be 1 over y times dy dx. Still implicit. On the right-hand side, the derivative of 4 natural log of x is 4 times 1 over x. The derivative of the natural log of some stuff. Okay, this one's still going to be kind of gross. The derivative of the natural log of arctangent of x cubed is going to be 1 over arctangent of x cubed times the derivative of the arctangent of x cubed, which is going to be 1 over 1 plus x cubed squared times the derivative of x cubed, which is 3x squared. Still pretty funky. So, right, it's 1 over the stuff, and then the derivative of my stuff is the derivative of the arctangent of x cubed. So when I'm thinking the derivative of the arctangent of x cubed, I'm thinking of it as the arctangent of some new stuff. The derivative of arctangent of x is 1 over 1 plus x squared. The derivative of arctangent of some new stuff is 1 over 1 plus that new stuff squared times the derivative of the new stuff. I know it's a lot to digest. The rest of this is not as terrible. The derivative of the natural log of cosine is 1 over cosine of x times the derivative of cosine, which is negative sine of x, minus 1/2 times 1 over x squared minus 7 times the derivative of that, which is 2x. We're not done. We have to bring the y back over to the other side. So then we'd have that our derivative dy dx, and I would, since I have to rewrite it anyway, I would simplify it. I'm going to write it as y times 4 over x plus 3x squared over arctangent of x cubed times the parentheses 1 plus x to the 6th plus, because it's a minus, 9 times sine over cosine is tangent of x. And then the 2's cancel, and you get minus x over x squared minus 7. And technically I'm not done, but I really don't want to write any more on this problem. The last step should then be to plug in the fact that y is equal to all of this hot trash right there. So the last step would be to write your answer as dy dx equal to x to the 4th times arctangent of x cubed divided by cosine to the 9th x times the square root of x squared minus 7 times all of the rest of this. That would be your final actual answer. It's terrible. I'm not going to write it. I'm really not. Try not to. Okay. So there's an example of logarithmic differentiation that to me feels unnecessary is probably the wrong word, because I think it's necessary here. Like doing it any other way would be worse, but it's not the only option. You could have done this directly by using quotient, product rule, chain rule a bunch of times, but this is the better way of doing it. The reason I bring this up is because we've talked about logarithmic differentiation before in other contexts. For example, a more typical reason or time you would need to use logarithmic differentiation is if you had something like f of x equal to x cubed plus tangent of x raised to the 2x minus sine of x power. Or as I like to say, when your function has an exponential vibe to it, and both the base and the exponent have variables. If either one of them is a constant, you don't need to do what we're about to do. Right? Just to kind of clarify here, right? If you have the derivative of, say, some funky stuff like x cubed plus tangent x to just a nice power, it's using the chain rule, right? It's going to be 5 times your stuff to the 4th power times the derivative of your stuff. Or in the other, whoops, who's calling? Yeah. Oh, is my phone not on silent? That's terrible. Okay, sorry about that. Or on the other hand, if you're taking the derivative of, say, a constant raised to the power of some funky stuff, then we would do the thing. I mean, you could do this one the long way, but we know that when you have a base other than e, the derivative of e to the stuff is e to the stuff times the derivative of the stuff. The derivative of not e to the stuff is not e to the stuff times the derivative of the stuff, which is going to be 2 minus cosine of x, times what else do I need since my base is 6 instead of e? No, it's been a while. I need the natural log of 6. Not that you couldn't do either of these with the method we're about to use, just that there are ways of doing them without that. Actually, this first one you would not use logarithmic differentiation for, but this one you totally could if you want to. Here, on the other hand, you're really, really stuck. We need to say that the natural log of f of x is equal to the natural log of x cubed plus tangent of x to the 2x minus sine x power. And then the reason we have done that is so that we can bring down the variable exponent so we no longer have a variable in our exponent. So we can rewrite this as the natural log of f of x equal to 2x minus sine of x in parentheses times the natural log of x cubed plus tangent x. And then we can differentiate both sides. The left-hand side, we're going to get 1 over f of x times the derivative of f of x. On the right-hand side, we have to use the product rule, among others. So derivative of 2x minus sine x is 2 minus cosine of x times the other stuff left alone. Plus, then we switch it up, and then probably not have enough room here. 2x minus sine of x times the derivative of the natural log of x cubed plus tangent of x, which is going to be 1 over x cubed plus tangent of x times 3x squared plus secant squared of x, which, yes, we can put in the numerator there. Normally, that's not what I would do, but you know, I'm running out of space here. And then lastly, we multiply both sides by f. So that f prime of x is equal to f, which is x cubed plus tangent x to the 2x minus sine x power. There's your f of x times all the stuff up here. 2 minus cosine x times the natural log of x cubed plus tangent x plus 2x minus sine x times 3x squared plus secant squared x over x cubed plus tangent of x. Kind of terrible. But not outside the realm of reason. Okay. I think that was, yeah. All right, we'll do one more. We'll do one more other thing, and then I feel like we should do a couple more graphing problems at least, because graphing's a thing. So I know that McDonough just started talking about the stuff we've been talking about today, right? The inverse trig stuff. Has Grobner talked about L'Hopital's rule yet? What? Or I guess he says, what did Grobner talk about in class yesterday? Concavity. Okay. Okay, cool. Right on. We definitely do want to get to L'Hopital's rule at some point, but that will probably be next week. But definitely it is worth talking about. It is a very useful tool we use quite often. But I had one more thing in mind. Oh yeah, I wanted to do. Okay. We got things to do. Let's do one related rates problem though, just because I know it's been a while and related rates is always kind of problematic or challenging. I will say, excuse me, very similar to related rates in that in the setup and the execution, optimization problems also have a very similar feel to them when you're trying to maximize or minimize some sort of thing based on a lot of words being thrown at you. So we'll get there in a little bit, probably next class. Let's look at this related rates problem. Yeah, I like this one. Sure. What do I got here? James, is flying a kite at a height of 40 feet, which seems like impossible to maintain a constant height if you're kite flying, if you're would not be super easy. I don't feel like you have to be good at it. The wind is pushing the kite horizontally, so not up or down, maintaining the same elevation at a rate of 10 feet per second. It seems pretty fast. I think it's not that fast. At the moment that the kite is 50 feet from James, how fast, how am I writing this exceptionally awful today? How fast does James need to let the string out? Which to me feels like a slightly clever way of saying, how fast is the distance from James to the kite increasing? Because that's what we're really asking, right? If I'm asking how fast am I letting the string out, I'm really asking how fast is that distance changing? All right, this definitely feels like it calls for drawing a picture. So let's draw a little picture here. So here's James. Here's his kite. Can I draw a kite? Maybe, sure. There's a little kite. And we know that the kite is always at a height of 40 feet. So that height's not changing. On the other hand, the distance, both the horizontal distance from James to the kite and the actual distance from James to the kite are changing. In our context, in the way this problem is written, and I know I really didn't. But based on the words I've written, is the kite moving away from me or towards me? There is a word in there that definitely, I think, decides which way it's moving. It's moving away from me. What's the word that decides that, in my opinion? That's not bad, actually. From is good. I was thinking actually the end where I say, how fast do I need to let out the string? I'm not pulling, if the kite was coming towards me, I'd have to be pulling the string in. But I also think the from, right? Yeah. Yeah. But yeah, really a better question should have clarified which way things are moving. This is really what I'm trying to point out here is that I didn't write the question maybe the best way possible. So sometimes you have to use context clues, or if this was on an exam, you might have to ask for clarification. Like, which way is the kite supposed to be, moving towards the person or away from the person? Sometimes it's okay to ask for clarification. It's always okay to ask for clarification. You just might not get any clarification if they think it is obvious to the reader. Okay, so we've got our system set up here. We've got the things that are changing labeled as variables. And then I'm going to write down that I know that the kite's moving horizontally. So I know that dx dt, the rate of change of the kite, is the horizontal distance of the kite is 10 feet per second. How fast the wind is pushing it. So it's moving, that way. And then I want to know how fast I'm letting out the string, how fast the distance from me to the kite is increasing. Now I need to find an equation relating the non-time variables. I've got a triangle. I should say I've got a right triangle. When you've got a right triangle, there's usually only one of two things it could be. It's either going to be some similar triangle stuff, which it's not, or more often it's going to be the Pythagorean theorem. Definitely the Pythagorean theorem. So we're going to have that x squared plus 40 squared is equal to z squared. And it is important that the things that are variables are written as variables and the things that are constants are written as their numerical constant value. So then when we differentiate both sides, the derivative of x squared is 2x times dx dt. The derivative of 40 squared is 0. Or you could say it's 2 times 40 times 0 if you wanted to, right? The derivative of something squared is 2 times your something to the first times the derivative of your something. But that seems silly. You should just write 0. Equals the derivative of z squared, which is 2z times dz dt. What's 40 squared equal to? Approximately. Actually, what is 40 squared? Yeah, what's 40 squared? Yeah, 1,600. What's the derivative of 1,600? Right, but it's a good question to ask because it looks like that could be something that's like, oh, it's like x squared. The derivative is like, why isn't the derivative 2 times 40? Because it's not a variable, it's a constant. It's the same reason that like the derivative with respect to x of e cubed is 0. There's no x's there. There's nothing that's changing, and if there's nothing that's changing, the rate of change is 0. Over here, we do have a derivative, 2z dz dt. Now, when I look at this, I know that I've been asked to find dz dt. So the one thing I've been asked to find is the only thing I'm not going to be able to fill in for. Everything else I should be able to fill in a value for. So I should be able to fill in that x is equal to, I don't actually know. I can fill in that dx dt is 10 feet per second. I can fill in that z is the length, right, we're talking about the moment that the kite is 50 feet from James. The distance from me to the kite is the z value, which is going to be 50. But I also need to fill in the x value. Well, to do that, I'm going to plug in the z value here and find the x value there. So we know that x squared plus 40 squared should equal 50 squared in the moment that we're interested in. Without doing any of the math, what should the other side be? In this 3, 4, 5 right triangle. Is it 3 though? It's not 3, it's 30. Right, because instead of a 3, 4, 5, we've multiplied every side by 10, and we have a 30, 40, 50 right triangle. Pythagorean triple. Or you could do the math, right? You could actually solve it and say x squared is equal to 2,500 minus 1,600, which is 900, and the square root of 900 is 30. But a lot of the time when you have right triangles showing up in these related rates or optimization problems, they're usually going to give you a nice perfect Pythagorean triple. So if you see like a 30 and a 40, you know the other side's 50. Okay, and so then we can plug in 30 here, and then we can solve for dz dt and get that dz dt is equal to 2 times 30 times 10 divided by 2 times 50. I guess I can cancel the 2's, and you have 300 divided by 50, which is equal to 6. 6 feet per second. That's your dz dt. All right. I have one over here. Good. Sure. So
let's slide back over to talking about some graphing. Unless there's questions about this I can answer. Oh, there was a follow-up. No. There was a follow-up question of this, which is how fast is the angle of elevation changing? Well, let's leave that one for never. So here's a question. I wouldn't bet on someone giving you all this, but you never know. Sometimes on a final, they'll ask you to graph the function that's kind of grossly rational. Oh, this one's going to be kind of gross. That's fine. X squared minus 8 over x minus 2 squared. And then they're going to be nice and give you the derivatives because they're kind of just terrible to find. So my derivatives are, they'll usually write it as a hint, a big hint. The first derivative is 16 minus 4x over x minus 2 cubed. And the second derivative is 8x minus 40 over x minus 2 to the fourth. You should never check these. They might be wrong. You should never check them. Because if they've written them wrong, they've done it on purpose, probably. I've actually written the wrong second derivative just to make it easier for people to find the intercept value, the critical value there. Because the actual second derivative, the critical value was going to be like 22.25. I was like, that's terrible. Let's just pretend like it's something else and no one will know. So if they give you this hint, just believe the hint. It's usually going to be right. Like usually people aren't doing stuff like that, but occasionally someone may. So graph, that word graph means a lot. That word graph means you have to do like 6 or 7 things kind of. So let's do all the things. And the order I'm going to do them in is typical. So first we're going to find the intercepts. Y-intercept. Great. F of 0 is going to be 0 minus 8 over 0 minus 2 squared, which is negative 8 over 4, which is negative 2. X-intercepts. We're going to set the function equal to 0. Setting a rational function equal to 0, you only have to worry about the numerator being 0, as long as the numerator and the denominator aren't 0 at the same time, which they're not. There's nothing that cancels and factors here. Factors and cancels. So we're just going to set the numerator equal to 0. And here we're going to get x squared equal to 8, or x equal to plus or minus the square root of 8. Which are not particularly nice x-intercepts. But they're not terrible. They're a little bit, right? So I'm thinking about this. I'm like, oh, well, my x-intercepts are essentially plus or minus almost 3. So a little bit left of positive 3 and a little bit right of negative 3. Because then the square root of 9 is 3 and the square root of 8 is less than that. It's about plus or minus 2.8. But again, we don't really need to know that. We just need to know it's smaller than 3. All right, I've done my intercepts. Now let's deal with the asymptotes. Some vertical asymptote. You're going to set the denominator equal to 0. And we're going to get x equal to 2. For the horizontal asymptote, there might not be any. So, and I said this before, I'm going to say it again. The y things, meaning the y-intercept and the horizontal asymptote, are usually easier to see if you have the rational function multiplied out. So instead of writing this as x squared minus 8 over x minus 2 squared, I'd really rather write it as x squared minus 8 over x squared minus 4x plus 4. And then it's easier for me to see that the degree on top and the degree on bottom are both 2, and that my horizontal asymptote is 1 divided by 1. The leading coefficient on top divided by the leading coefficient on the bottom. My horizontal asymptote is y equal to 1. We've dealt with all the original function stuff. Now we're going to deal with the first derivative stuff. I would say I would never ask you to identify where a function is increasing or decreasing. I don't feel like that's, I feel like you're doing that anyway when you're finding where you have your relative extreme. That said, someone else could ask you to do that. So let's do the first derivative stuff.
Oh, look, we've already found the first derivative. It was given to us. So we're just going to take our first derivative, 16 minus 4x over x minus 2 cubed, and set it equal to being either 0 or undefined. Let me ask everybody to show me on your fingers. What value of x makes this expression undefined? Yeah, thank you. Yes, 2. So we know that x equal to 2 is going to be on there. And what makes this equal to 0? You could also show me on your fingers, actually. Yeah, it's going to be 4. I would actually prefer to write this as 4 times 4 minus x over x minus 2 cubed. So it's a little more obvious that x equal to 4 gives me. Yeah, we'll get there. Okay, so then I'm going to put those critical points on the number line. Just those critical points and nothing else. And also, this is why I like to have my first derivative factored as much as possible. It makes it easier to see where the derivative is going to be positive and where the derivative is going to be negative. So pick a number larger than 4, like 7. 4 minus 7 is negative. 7 minus 2 is positive. A negative divided by a positive is negative. And then you can either keep picking points like we do, or you can say the 4 came from the 4 minus x, which is raised to an odd power, so the sign is going to change. The 2 came from the x minus 2 to the third, which has an odd power, so the sign is going to change. Or you can pick points. You can pick 3. 4 minus 3 is positive. 3 minus 2 is positive. And positive divided by positive is positive. You can pick 1. 4 minus 1 is positive. 1 minus 2 is negative. A negative number cubed is still negative. So it's going to be positive over negative, which is negative. But I like doing it, looking at the powers of the factors, but I think it's faster. Okay, all right. Do we have a relative maximum? Where is it? Two or 4? Definitely 4, right? Because the function is, I didn't draw the thing. Sorry. I always go decreasing, increasing, decreasing. Now it's easier for us to see, we have a relative maximum of 4 because the function goes from increasing to decreasing. Do we have a relative minimum? No. What do we have at x equals 2? A vertical asymptote, which precludes anything else from happening there. So what I would recommend is when you're over here doing this. Oh, shoot, I forgot to plug in my thing. Sorry, 1 second. Don't want to lose this. Feel real smart here. Save. Okay, got it. All right. So at 2, we know we have a vertical asymptote. I might even just draw the vertical asymptote in right there to remind myself. You might ask the question, do I actually need to include 2 on the number line here? The answer is a resounding yes, because the sign changes from the left side of 2 to the right side of 2. But 2 can never be a critical value because it's not in the domain of the original function. So if someone ever asked, which I think is kind of a not nice question, if someone asked to name the critical points here, the only true critical point is x equal to 4. X equal to 2 is not by definition a critical point, because the definition of a critical point is a point that's in the domain of the original function, where the derivative is either 0 or undefined. That said, we still treat 2 like a critical point, and we use it in all the ways we would use a critical point, except it can't be where you have a max or a min. So I shouldn't say nothing. I should say we have a vertical asymptote at x equal to 2. So to have a relative maximum at x equal to 4, I should plug 4 back into the original function to find the y value. So x equals 4 and y equals f of 4, which is, looking at my original function here, 4 squared minus 8 over 4 minus 2 squared. That's 16 minus 8 over 2 squared, which is 2. Cool. So my relative maximum is at the point 4, 2. Let's find the second derivative stuff. I will also point out that for this first derivative, you could also say the function, if you were asked, you could say the function is increasing on the interval from 2 to 4, and decreasing on the interval from negative infinity to 2 union 4 to infinity. Usually you're not being asked to state this, but you could be asked to state this. All right, second derivative stuff. Let's go ahead and factor the top and say that the top is 8 times x minus 5 over x minus 2 to the fourth. And we're setting that equal to 0 / undefined. We're going to get x equal to 5 and x equal to 2. And again, just like before, 2 is not a real critical value, but it's still going to get included on the number line. Ooh, yeah, and actually this brings up an important point. So let's say if I plug in the number larger than 5, like 6, top is positive, bottom is always positive, so it's definitely positive. And then at 5, the 5 came from x minus 5 to the first. The odd power means the sign changes. The 2 came from x minus 2 to the fourth. The even power means the sign stays the same. If I was talking about concavity, I would say it's concave up on the interval from 5 to infinity. Maybe I should draw my little picture here. And it's concave down on the interval from negative infinity to 2 union 2 to infinity. We don't get to include the 2 there because the function's undefined at 2. All right, and I guess I have an inflection point. Where is it? X equal to what? 5, right? The place where the concavity changes and the function is defined. And we should find the y value. The y value would be f of 5, which plugging back into my original function, which I've lost now, f of 5 is going to be 5 squared minus 8 over 5 minus 2 squared, which is going to be 25 minus 8, which is 17, over 5 minus 2, which is 3 squared, which is 9. Just a little bit less than 2. Yeah, question. Sorry, thank you so much. Yeah, because from 2 to 5. Good call. Let's write that again. Oh my goodness. Thank you. Let's appreciate it. See, it's really easy to make stupid mistakes. Try your best not to. Okay, so I think we've gathered all the information we can about this function. Now we're going to graph it. And when I'm graphing it, the thing I'm paying the most attention to after I plotted everything is this first derivative sign chart. Because this is telling me the function's going down, then up, and then down. That's what I'm looking at. Okay, so let's plot all of our stuff. Oh my gosh, come on. Sorry, it's always a challenge here. Okay, so I make it look nice. So let's see, looking back to my list here, I have a y-intercept at -2, a x-intercept at plus or minus √8, which I know is a little bit smaller than 3. So like right there-ish and right there-ish, because it was positive √8 and negative √8. And then I have a vertical asymptote at x equal to 2. Horizontal asymptote at y equal to 1. And then first derivative stuff, I have a critical point, a relative maximum at 4, 2. And I have an inflection point at 5, slightly less than 2. Right? It's 5, 17 over 9, which is a little bit less than 2. Also, it should be less than 2, right? If that's a relative maximum, this point here probably shouldn't be higher than it since it's pretty close to the neighborhood that it's in. All right, and now to graph this, I'm going to try and hit all those points, adhere to the asymptotes, and follow the fact that I'm going down, down, down until I get to 2, and then up after 2 until I get to there, and then down after that. I think I can do it here. Let's see, we're going this way. Hit there. There. So there's my decreasing from negative infinity to 2. And it's also concave down as it should be. And then from 2 to infinity, sorry, from 2 to 4, the increasing. So I'm gonna go like this. Topping out, and then decreasing, and then concave up. Cool. And then we could label things if we wanted to. We probably don't really need to since we've already figured them all out from before. Say that one more time.
What did you mean by that?
Well, so I know that it's supposed to be concave up because we did the sign chart. So it's concave down here, it's concave down here, it's concave up here. Now, it's kind of hard to see the concave upness, right? Like it doesn't really look up like a cup. The other way to think about concavity, and this is something I learned only in the last few years, but I think it's super neat, is that if a function is concave down, any tangent line you draw should be fully above the function. So just to kind of show you, in these concave down parts, like right here where it's concave down, this tangent line is totally above the function. Or over here, right where it's concave down, this tangent line is completely above the function. Whereas somewhere right there, it changes from being concave down where the tangent lines are above to concave up where the tangent line is below. Your graph doesn't have to be perfect. But the thing is, right, you couldn't continue being concave down and also flatten out to this horizontal asymptote. So eventually, because of that having to flatten outness, you have to then change your concavity to get that behavior. The only other thing I will say that someone could ask you about for this particular example is, where does that graph cross its horizontal asymptote? Because it certainly does, right? We had no choice but to cross it. Well, that's easy to find. The horizontal asymptote is y equal to 1. So you literally set your function x squared minus 8 over x squared minus 4x plus 4 equal to 1, and then solve. So we'd have x squared minus 8 equal to x squared minus 4x plus 4. The x squareds cancel. Add 4, or sorry, subtract 4, you get negative 12 equal to negative 4x, x equal to 3. So this point right here, this point where you cross the horizontal asymptote is 3, 1. It's kind of cool. People don't usually ask that, but I think one of your teachers did ask that on one of your exams, so just something to be aware of. All right, that's all I have, which is good because it's 2:30.